Okay, yeah, thanks everybody for coming out. So, I'm glad to be here at the first sort of inaugural talk for this conference, and I was asked to come present something on machine learning, so I thought it would be fun in the time slot I had just to go over some common errors in machine learning. Hopefully you can avoid making some of these, or learn from them, or make them on purpose. If you want to mislead people, your choice. I'll just go through them. Some of this was at least loosely inspired by a blog post by Shantao Xu, and I got to interview him about it on DataScience. He put together some initial thoughts on mistakes people make. So some of my slides echo his sentiments, but I've added a few others of my own, and I'm eager to hear from anybody who has other ideas, maybe expand this into a longer thing, and really collect sort of a taxonomy of common mistakes we can all look out for. I split these, so we're going to go over, 14 of them there, or 12 of them there, into basic areas. So basics, these are ones where I would say, you have just enough knowledge to be dangerous. You're able to run machine learning code. You may not necessarily know the algorithm, but you're producing results. This is probably the area where your risks, the risks you have for making mistakes are broadest, because you present a model that may have some intrinsic flaw. So hopefully I can share some really important gotchas to stay out of the way of that. And if you find yourself at this basic level, because I know we've got a wide spectrum of expertise at the conference, I think the key for me is to always think scientifically about your black box solutions. So let's say you produce a model, support vector machine maybe, you don't yet understand kernels and things like that. I mean, one could build an argument that says, hey, you shouldn't be using support vector machines, use something else, but no matter what, machine learning is trying to do something that the scientific process can measure. So if it's classification, you're making classifications. You're looking at new examples, and you can evaluate the output of the model. So there's always an opportunity, even if you don't have the deepest insight, to look at these things empirically and use your brain power and try and break down what's the model actually doing, what are its flaws, and things along those lines. Intermediate for me is when you've developed really good instincts on the methods. You know the algorithms and the techniques fairly well. You've got some experience with them, and you're able to penalize effectively and tune your models. And by that I mean, you're not just taking out-of-the-box things or playing around with parameters, but you understand grid search and techniques like that to the point where you can really control the tools at your disposal. In advanced, I've only got two, either because at the point of being advanced you ought to know this stuff, or maybe because I myself am just getting into advanced tools. But I consider advanced topics to be where you have really a mastery of the methods, and you're pushing the information theoretic limits of what's possible, that you start to think about the bits of information in your data set and what you can extract from them. So I'll break them down in these three ways. First one I want to talk about is the linearity assumption. And this is perhaps the one I see most often made by mistake, especially by people I mentor or see in boot camps and things like that. So to get started, let's just talk about this table here. I put this in what's now being called the tidy format. Tidy is very simple. In case anyone doesn't know, I'll explain it. The basic idea is that your rows are observations and your columns are your variables. So that's all tidy is. Nonetheless, you should go read the paper Hadley Wickham wrote on it. It's about 22 pages somehow, but it goes into a lot of great details about why this is an important format, why tools are built around it, but fairly intuitive concept. Rows, observations, columns, variables. Here I have some fake medical data. So I've got a patient's temperature, their heart rate, and whether or not a doctor identified them as healthy. So this, of course, is our objective function. We would love to be able to predict whether or not someone will be healthy based on these two measures. Now, in general, a problem like this, you've probably got a lot more sensor data. You've got longitudinal data. I've simplified this for the case of explanation. What you see here is sort of an intuitive thing that we all kind of know. A healthy person's temperature ought to be around 98.6 plus or minus, give or take something. So someone who has a very low temperature is probably not healthy. Very high temperature, same story. If you were not to be aware of that and not consider that, and you went just did a simple logistic regression, you wanted to predict healthy patients based on an intercept and some multiple of their temperature, this is a fine statement of a machine learning problem, and you can use optimization to solve this problem and come up with the ideal coefficients that, when multiplied by the temperature and added the intercept, and then run through the logistic function, gives you some classification as to whether or not the person is healthy. However, the problem here, if you treat this linearly, as this does, you can only separate this data to be above or below. So you could eliminate, maybe say anyone above a certain temperature is unhealthy, anyone below it is, which of course would overlook people over here, or vice versa. you'd say there's a lower point temperature, and anyone below this is not healthy, anyone above it is. This is not a linear problem because we have this bimodal system. Now there's a trick you can use. I think I first learned it from Dr. Richard Golden on the Learning Machines 101 podcast. The basic idea is, how could we transform this into something linear? Well, you could subtract the mean value, 98.6, and then take the absolute value. And that would give you a linear separation of this data, that the further away that number is from zero, the more likely that person is to be unhealthy. So this is not unavoidable. If you do a lot of feature engineering and data munging, you can get around that, but it's not a given. And a common mistake I see a lot of people make is they think they're done when they've got data in a tidy format, slime it through a machine learning algorithm like a sledgehammer and see what comes out. If you have any nonlinear data, your problem will suffer from this. People will sometimes say tree-based methods, like CART or random forest or C4.5, are a little bit immune to that. And there's some truth in that. A tree-based method could split, above or below a high temperature and then split again on one side above or below here, but it still is not guaranteed to deal with nonlinear systems. So something to always be looking for in your data. Moving on, one of my favorites, leakage. So here, let's say we were going to try and predict who's going to win the Olympic figure skating medals. So an important variable would seem is how many hours a week they practice, the years of experience the trainer has. Maybe these contain some predictive power now, we don't know. Then there's the score they achieved from the judges in the Olympics and whether or not they got a medal. Now, of course, if you know the score, predicting the medal is pretty trivial because they're highly correlated. Not only that, but it's useless because you don't know that score until the time at which the prediction is no longer helpful. If the medal's been awarded, or is maybe momentarily about to be awarded, then the prediction doesn't allow you to take any action. Machine learning models should produce something that can be used to inform a decision or be smarter. So you would need to remove a column like score from your data set. This one's fairly obvious and on purpose for demonstration's sake. But what you'll find is leakage can occur in unexpected ways. Time is often a significant component. Looking at older customers versus newer customers, the older customers have had a lot more time to exhibit different types of behaviors. So even unintentionally, you can often have a lot of leakage in your systems. Data cleansing failures. So this is one of the 4 plots from the famous Anscombe's quartet of some series of data. Now, to our human eyes, it's fairly obvious this is some sort of outlier and probably does not fit this pattern. Yet, if we were to do a simple ordinary least squares regression to it, this is the model we'd come up with. That is the line we would fit. And the reason for that is because we're trying to optimize, or to minimize the loss, the error between the actual data and the observed data. And in order to balance out a little bit for this outlier, we're pushing the line up proportionately to balance for it. When realistically, what you probably want to do, depending on the context of your data, is eliminate that element entirely. So unless you're doing proper data cleaning, you're likely to come up with a spurious model or a model that's at least weakened in certain ways. Class imbalance. This actually is the one I see most mistakes with, although I think I said that on the last one. Class imbalance is where you have a minority case you're trying to detect that is fleetingly small, or at least just smaller than the average. So this might be some sort of fraud detection problem. So this is some subset of credit card data, the store at which the charge took place. This is important because we know that places like gas stations are a lot more frequent for people to try and commit fraud. So United Oil might be classified into gas, and we would keep in mind that we see a lot more fraud historically from gas stations, whereas Roto-Rooter is probably a service that's provided on-site by a professional who engages with a homeowner or a renter or a landlord or whatever. So while there could be fraud there, it seems a lot less likely. Similarly, distance from the home, that is the credit card holder's home to the location. If a charge happens in a city thousands of miles away, that's a lot more suspicious than a charge, down the street from them at the gas station or whatever. So certainly these are variables we want to consider that might be informative for fraud. But as you look through this, what do we see? I have one case of fraud and a lot of no's, which is very typical. The majority of credit card transactions that go through are not actually fraud. We might be dealing with 1% or sub 1% of transactions. So if 1% of your data set is fraud, you can easily build a 99% accurate classifier. You know how? You always say it's not fraud, and you'll only be wrong 1% of the time. But of course, that 1% is the interesting case you're actually trying to work on. I should tell you about some solutions. So class imbalance, the typical way around this is either to reweight your data set, to oversample, or balance the training in some way. Different algorithms respond differently to different types of techniques, so I don't know that there's one clean, obvious solution, but certainly you need to be aware that class imbalance is out there, and the types of accuracy and precision and recall you'll get on your models and your other diagnostics can look a lot better than they actually are if you don't consider this. So mishandling of missing values. One of the first lines of code I see in a lot of data analysis is either fill NA or drop NA. Where do we have NAs here? Well, we have NAs if this were some sort of, let's say, loan default prediction. So we know the issuer, the person's income, whether or not they own their home, and did they default or not. So this would be great for a bank, right? They would love to predict, will someone, based on what we know about them now, later default on their loan. However, if we drop the two NA rows, we'd be eliminating the Ponzi Bank and the Madoff Trust, which are, in no coincidence, since this is a contrived example, those are the two that eventually defaulted. So, again, there's no necessarily certain way that you want to handle these. It's just to say that removing data is removing information. So you could perhaps deal with these by creating a three-class system, yes, no, and unknown. Maybe you need to ask some data governance questions. Where did this data come from? Why is it missing? Can we recover its value, or should we impute it? Things like that. Dropping can be the answer, but is not necessarily the solution to missing values. Overfitting. This is a classic one anyone working in machine learning should know a fair amount about, so I won't go into too much detail, except to maybe explain my figures. If this is a tree-based model, one in which you start here, you split out some criteria, maybe for the first example, temperature less than X, go here, temperature greater than X, go here. If you allow your tree to have infinite depth and infinite leaves, it may not choose to do that, depending on the split criteria you establish. It might stop at some logical point, but there's not necessarily a built-in reason why the algorithm will constrain itself to a limited complexity model. Similarly, in a regression type approach, if the dots are our data points, the simple linear fit here, well, it doesn't hit all of them. There is an error between the prediction and the actual data. Running a connect the dots sort of simulation, this, maybe 8 or 9 degree polynomial fits all the dots, has no error, but of course does not generalize beyond your training set. So this tends to come a lot. I think there's a great deal of attention paid to overfitting, so I don't see it as often as you might expect. The case I see it when people don't know they're doing it is when they have a really large volume of feature sets available. Maybe you would separate your data by like day of the month effects, so you want to include what happened on day 1, day 2, up through day 31, or even day of the year. Sensor data and different telemetry can often give you really wide feature sets. So if you have really high dimensional data and not as many observations, you're dangerously at risk of overfitting, even with a lot of observations. Just the fact that you could have some sort of encoding built in here where one feature gets to an extreme value in rare cases could end up giving you some overfitting. Lastly, I think there's two more, the basic one. Assuming a representative sample. So if you're dealing with, especially retail or any general business that asks you to apply machine learning to study their customer base, there are a lot of common and interesting problems here. What customers will churn out next month? Because perhaps we can intervene, get that person to stay around longer. What customers could be susceptible to an upsell? These are really interesting and useful business questions. And you will have training data, of course. If you want to look at churn, you can look at current customers and who stays. Maybe there are certain properties of customers that stick around. You can look at former customers and see if there are common features that predict who will leave your services. What you can't really do is look at people who never became a customer. So your data set is inherently limited in this respect. You can't know who you didn't capture. So to assume that a model built on the data you have describes the entirety of your possible customer base is a mistake. It may be that people will never be a customer for some legitimate reason. Perhaps you can observe it and build it into the model, but nonetheless, you don't have a lot of data on them, therefore you're training it on a known to be somewhat incomplete model. This is an important one. Not knowing your algorithm well, and I see this a lot in people who are just getting into machine learning. How many people know k-means clustering? Very common algorithm, yeah, lots of hands. I think it's one of the first things that gets taught in maybe week 1 or week 2 of a lot of machine learning courses, especially because it's the classic unsupervised learning algorithm, and unsupervised is definitely a growing topic in ML. What is not often taught about it is what it's doing under the surface. So K-means is assuming that all your data is essentially Gaussian blobs, Gaussian being, like the bell curve, but multidimensional. So that all your data is clustered together in these Gaussian blobs around however many dimensions you have. In this case, here we have some fictitious data on cars. So we have the cost of the vehicle and the number of previous owners. Maybe we're trying to group together something about resales. Well, the scaling here is the problem. The cost of the vehicle in increments of $1, $1 is not significant. If I was going to buy a car for $1,200 and somebody said, no, it's got to be $1,201 or the whole deal's off. It's not worth my time to walk away from that. Much as I don't want to get squeezed for the extra dollar, I paid more in transportation to arrive to do that transaction. So I'm going to go with it. $1 doesn't mean a lot to me at this scale of money. Yet number of previous owners, the difference between 1 and 2 is very broad. It's much bigger than $1. Yet numerically, it's the same. So if we ask K-means to run on this with just a K of 2 in this case, it's quickly going to separate the data right here down the middle and based only on the cost of the vehicle. You can see it's totally independent of the number of owners. This actually has no bearing on the analysis whatsoever. Even though I can plot it, it makes a nice pretty plot, you can see that regardless of the previous ownership, we're split here. The decision rule that separates these has them totally independent. So that's something that you're looking for as you visualize it. Is there actually any dependency on your data? More so than that, I had to pick K equals 2. Now I could have picked K equals 4 and what might have happened. Maybe we get these rows as clusters or something along those lines, or we get more vertical bands. But even in picking that, another observation about K-means is it has some balancing criteria built into it. It's constrained to not create a lot of clusters that have a small amount of data, like 1 or 2 data points in it. So just because you have that constraint in there that's built into the algorithm, you're sort of forcing this to put a dividing line down the middle so that you get a centroid here and a centroid here. So this algorithm is very much artifacting this data set. And since it's unsupervised, it's not always easy for us to see that. We have to ask a lot of questions about, why did we get the result we got? Is this truly what we want? And maybe as you get along in ML, you find ways to penalize this or tune it to get the result you're actually looking for. So summarizing the 8 basic ones that I thought I see commonly in a lot of people just getting into ML, that linearity assumption. Rarely do I find data to be linear in practice. Sometimes, yes, sometimes in certain telemetry, but most often you're going to have to transform your data or at least deal with this. Leakage is one that shows up in surprising places. A lot of the common leakage examples like mine are sort of more boneheaded mistakes. You included an ID or some feature that is obviously predictive of the outcome. But this can be subtle too. I remember a case where we were trying to predict customers that wanted to cancel a subscription for an online e-commerce business, and we were looking at web traffic, like where did people go on the site? We went and read the CEO's bio. Okay, that's interesting. Maybe you're more invested in the company. You went and checked my account and changed your password. That seems, perhaps that would be indicative of good, customer long-term behavior. You went to the customer service page. Oh, well, that's interesting. Why are you there? Does that mean you're having a problem? Or did it mean you went to that page because that's the first page you go to cancel your account, and therefore a moment later it'll be canceled for some subset of those people, thus putting some leakage in your data. Data cleaning is one that's hard to pin down an exact example of, except to say that if you don't know your data set extremely well, you shouldn't yet be throwing algorithms at it. Make sure you are not surprised by what's coming out. You should have a pretty deep intimacy of what your data set is telling you and do a lot of exploration. Class imbalance is key. If you're trying to do classification or prediction onto some groupings or some categories, and you have one that's the smaller case, as is very often true, you're often trying to predict fraud, predict people who are going to be susceptible to upsell, things like that. You're looking for a minority case in general, and that means that inherently you have a class imbalance. Missing values, not necessarily the right case to drop them. Overfitting, I think most people are aware of. The representative sample is one that's hard to pin down, but just kind of a gotcha that you're thinking about, and not knowing your algorithm we just went over. So let's get into some more intermediate ones, or what I consider intermediate. Your mileage may vary. Perhaps you'll have the opportunity to make these sorts of mistakes at different points in your career than I did, but experimental design errors. Non-random A/B testing. So I think it's pretty clear most people who deal with data know that you want to do some amount of testing. even when the model gives you good predictions and you're happy with your accuracy and everything on your training data, you've done cross-validation and things are looking really good, you've got some high 90% accurate model, the executive team's all excited, let's roll it out. Well, there's no guarantee that when you roll it out, that A, the user base doesn't respond to that and change the behavior, and B, that your training data is truly representative of your sample. So you definitely need to do A/B tests to validate anything that you've developed that you want to get some actionable insight out of. But A/B tests have to be really well randomized, and sometimes it takes a statistician to do that. Not always, but sometimes. What tends to creep in here is you'll have outside business constraints trying to emphasize how an A/B test goes. They may say, well, okay, you can A/B test on 10% of the population, but don't use anybody from our major traffic supplier. Well, if it's your major traffic supplier, that's the majority of your business. If you can't test on them, you're not necessarily going to learn anything because we don't know for certain that the major traffic provider gives you the same traffic as the rest of the traffic providers. So you really need true randomization, and sometimes you'll have to educate your executive team on why that's important and why you have to have some even split. Doesn't mean the A group can't be 90% of the traffic and the B group be a very small risky percent, but you have to have properly designed A/B tests. Along those lines, user leakage is something we don't hear a lot about, but it's out there. Let's say you wanted to create a program, or you were asked to help engineer a program that built a referral system for a business. So existing customers would be given discounts or bonuses or something along those lines if they were willing to refer a friend and that friend signs up and stays for 30 days or whatever, something along those lines. If that person in the A group gets someone to sign up, that new user is not exactly the same as old users. So if they go into the B group or the A group, they've kind of leaked out, they're a product of the experiment from the A group, but they could leak into either the A or the B group and really change the measurements you're getting from that experiment. So user leakage comes up in cases where you're trying to generate downstream effects from some sort of experiment. Insufficient controls. This is where you roll out a lot of tests and you don't really measure a baseline. So someone might say, hey, let's try different colors and fonts on the website. And you come up with 60 different permutations and you run them all and see, oh, I don't know, this one seems to be the winner. I guess purple and 14-point font is what's right because that had a slightly larger conversion rate than everybody else or slightly higher click-through rate than everybody else. Actually, that could be a problem of failing to control for multiple comparisons, which I didn't include in the, oh, I didn't, sorry. Failing to control, so let's jump to that one. Multiple comparisons is where you run lots and lots of tests. Now, someone has to win. If all of us decide after this event to go out into the quad and run a relay race, there will be a first place winner. That doesn't mean that person needs to go to the Olympics. It just is because there has to be a first place, just as there has to be a last place. So, in not controlling for multiple comparisons, you could arrive in a situation where you have some spurious results. You've detected that a certain button color, shape, size, position wins or appears to be the best because it's a small advantage over the others, not a real one. Insufficient control is where you don't have enough of the baseline measurement. And lastly, I would say death by 1,000 slices. This is the last one under experimental design errors. This is where you do some test, and as is often the case, your test arrives at nothing. You tried a bunch of different email subject lines or page layouts, and they all perform the same, which probably tells you that your business is well optimized or that your business needs some major sort of quantum leap to get ahead. If they're all performing about the same, what you should say is, hey, we failed to reject the null hypothesis. So if there is an effect, there's not enough data here for us to even measure its precision, and if the effect size is that small, it's probably not worth chasing. But what can sometimes happen, especially by people who don't have the same sort of analytical background as a lot of people at this conference might, is you start diving and you say, well, what if we just look at people from the Midwest and just people over 50, and you end up with these convoluted statements of men on Wednesday afternoons who like golf will convert 10 times higher than anyone else. And while that may be vaguely true, or you may have some data that appears to support that, it's death by 1,000 slices. You've just segmented the data enough until you've squeezed water out of a stone because you didn't want to come up empty. Coming up empty might seem disappointing, but ultimately that's a good result. That probably means you have a well-optimized area of the business and it's time to chase something else. Inappropriate interpretation of model parameters. So a lot of why certain machine learning models appeal to people, things like logistic regression and decision trees, are because we can look at them and sort of derive some idea about them. This comes from the famous golf example that is used a lot in explaining trees. So there are things like the weather outlook and the humidity and the wind factor, and we're using this to predict whether or not people are going to show up to play golf that day. This would be useful to a golf course who wants to staff appropriately or manage the grounds appropriately or whatever the case may be. But you can also wind up in situations where you misinterpret these parameters. So if it turns out that having a low humidity is really good for golf, the conclusion is not to put dehumidifiers on the golf course. This is to say, hey, this is a nice situation that if nature is so kind to us, we benefit from, but it's not something we can control. Heteroscedasticity. Now, this gets ignored a lot because, frankly, a lot of methods are robust in this. Maybe I should define it. Heteroscedasticity is the process, or is the situation where the variance is not constant across some variable. So here, some x-axis, as it gets greater, the variance starts to grow a lot more. So, as I mentioned, a lot of algorithms are somewhat robust to this. But what it tells me when I see something like this is there's a signal in my data set I failed to extract. Something is available that explains why this variance is increasing, and I wasn't able to decompose it out of that time series, or I wasn't able to include the right feature that helps reduce that. So when you see heteroscedasticity, it's kind of, to me, an indicator you should be looking for more. Maybe you've missed something, or maybe there's a variable unavailable to you. Failure to regularize correctly, and I'm running a little short on time, so I won't be able to do this one total justice, but a basic principle of machine learning is you have some set of features, your design matrix, or your X matrix here, times your weights that you've trained, or this is what you're going to train. You're going to minimize W such that when you multiply your features by those weights and you subtract the actual known values, you want that as close to 0 as possible. But those can go to extremes, in which case you'd want to penalize them. Here's an example of something extreme. Maybe the estimated purchase price, you develop a model that seems really good. It says it's minus $1,000 for every mile on the odometer, plus 100,000 times the miles per gallon of the gas. And while that might work out coincidentally in a very fine band, it's obviously nonsense. No single mile on the odometer could be that sensitive to the purchase price. So you want to penalize for how extreme those weights are. The two most common penalizations are L1 and L2, the last one on Ridge. There's also Elastic Net and a couple other really useful ones. Subject to look up at some point if you're not familiar with it, especially if you find extreme coefficients in your data. So my 4 intermediate ones, let's jump ahead since I'm running short on time to my 2 advanced ones, or what I consider advanced ones. So, not understanding Goodhart's Law. I just did a talk all about Goodhart's Law at the DataScience pop-up that Domino hosted. That video is going to go online, so if you'd like to follow me on Twitter, I'll post it. You can see the whole chart, the whole talk at some point. But the nipple version here is that when a measure becomes a target, it ceases to be a good measure. So everybody knows about FICO score, right? We'd all like to have a high FICO score. I happen to know that FICO score is partially based on the length of time you've had certain credit, which is intuitive. It makes sense, right? If you've had good standing accounts for a long time, that shows you to be have a history of good reputability. Except for I have a credit card from a company that I consider unreputable. I don't want to do business with them anymore. And rather than cancel it like a normal person, I keep it open and I stick it in a drawer because I'm trying to manipulate that algorithm. I know how it works and I want to have good credit, so I'm altering my behavior to work within that system. You see this a lot, especially when money gets involved. If someone can earn money, either by putting ads on their site or things along those lines, as soon as there's a target you're after, someone will try and manipulate it. So while you might do a great job building a machine learning model that absolutely fits with the training data, the minute you release it, you've changed the world in a small way. Just a little world in which your model's affecting, but you've changed it nonetheless. And if you don't understand Goodhart's Law and know that this could happen, you might become a little bit willing to accept that a model is drifting when it's not. Lastly, losing sight of the business use case. And this is the one that I see very smart people sometimes making, which is why I put it as my last one. I've had people come to me and say, wow, I started looking at this problem and I think we've got it all wrong. I think my PhD thesis is exactly what we need to fit this problem. And while that would be a great coincidence, it's not necessarily always the case. And while we'll learn about new techniques, most people, myself included, are very excited about deep learning and a lot of the stuff that's becoming very lucrative and powerful and showing up as we get a lot more commodity hardware and high-performance computing making these things available. But just because you fall in love with a technique and it's powerful in one domain does not mean it suits the use case you have in front of you, nor does it mean that the business you're working for, the organization, has an appetite for that, or that waiting a year to develop the most apt model is going to be as effective as getting out something simple and iterating quickly. This can be disheartening because we spend a lot of our time getting really good at advanced techniques only to find that, hey, it's the simple ones that often matter. Summary of my last two advanced ones. I'm running pretty short on time. Don't know if we have time for questions, but I am definitely available on social media and whatnot if anybody wants to follow up. I'd love to hear your stories about mistakes you've made or how you found and corrected them. These are my words of advice. Never stop learning and reading papers. There's a lot going on in machine learning, and that's not going to slow down anytime soon. Always know your data set intimately well, and spend 20% of your time trying to break your own model. Think of yourself like a hacker and say, all right, if I were an adversary on the outside of this trying to defraud or manipulate the business I created this model for, what might I do? How could I break it? That, in my opinion, is the best place to find your strength. So, like I said, I host a Data Skeptic podcast. You can check us out at dataskeptic.com or follow me on Twitter here. Thanks a lot, everybody.